Induced EMF. You will be aware that when a current flows, a magnetic field is produced. Well, also, when the magnetic flux through a coil changes, an EMF is produced in the coil. Here we have a solenoid producing a weak magnetic field, and here we have a conducting loop enclosing some of the field. If we increase the current through the solenoid, we get a stronger field, and there is now a greater magnetic flux passing through the coil. As the magnetic flux is increasing, an EMF is produced in the loop, and as it is a complete circuit, a current will flow. When the flux stops increasing, the EMF is zero, and so the current in the loop will stop. The faster the magnetic flux changes, the greater the EMF, and so the greater the current. The direction of the current is such that the magnetic field it produces opposes the change. So this loop had a weak magnetic field going from right to left through it, and now it has a stronger magnetic field, more flux, going from right to left. So the way it can oppose that is by having a current running in this direction round the loop. Using the right-hand grip method, you can soon establish that the magnetic field produced by this current will go left to right through the centre of the coil, opposing this increase. If the flux is reduced, the current in the loop would reverse to attempt to maintain a field going from right to left through the loop. It doesn't matter how the flux through the loop changes. Here we have a bar magnet, and as we move the loop towards the magnet, the flux through the loop has changed. As the loop moves towards the magnetic flux through it increases. An EMF is produced, and, as it is a complete circuit, a current will flow. When the movement stops, there is no longer a change of magnetic flux, and the current stops. The faster the movement, the greater the EMF, and so the greater the current. Incidentally, we could have equally moved the magnet towards the loop. Here, the flux going right to left through the loop is increasing, so the current in the loop will produce a field going from left to right, meaning a current again going in this direction. If the loop is moved away from the magnet, the current through the loop would reverse. Another way of changing the magnetic flux through the loop would be to tilt it, like this. As we tilt the loop, the magnetic flux through it reduces, an EMF is produced, and a current will flow. The faster the loop is tilted, the greater the EMF, and so the greater the current. If we'd replaced the single loop in the previous experiments with a double loop of the same cross-sectional area, like this, the same flux changes would have produced double the EMF, and so double the current. A property called the flux-linkage tells us how a coil connects with a magnetic field. And flux linkage is equal to n phi, or capital Phi, flux linkage, is equal to n times lowercase phi, the magnetic flux. Or we can write phi is equal to BAN, as magnetic flux is equal to magnetic flux density B multiplied by area A. In this equation, n is equal to the number of coils. As the number of coils has no units, the units of flux linkage are Webers, the same as the units of magnetic flux. Another way of inducing an EMF in a conductor is to cut through magnetic field lines. Here we have a wire, and we can move the wire through the magnetic field like this. As the wire moves through the field, it cuts through field lines, and, as I said, an EMF is induced. As there is not a complete circuit in this case, no current can flow. If the wire moved back up, the EMF would reverse direction. The faster the wire moves, the greater the EMF. In this case, the direction of the EMF would produce a current experiencing a force opposing the motion, and by Fleming's left-hand motor rule, you can work out the direction that current would be in. The magnetic field goes from north to south, So if you point your first finger of your left hand in this direction, the wire was moving down, so the current must experience a force upwards. So if you direct your left thumb upwards for the motion, your second finger representing the current will now be pointing towards you. So using Fleming's left-hand rule, this requires a current coming towards us. If the wire was now moved up, the current would move away from us, giving a downwards force. Of course, in this case, there is not a complete circuit and no current flows, but the EMF induced would be such as to cause the correct current flow, being positive at this end as the wire moves down, and positive this end as the wire moves up. If the force on the wire had been in the same direction as it was moving, then the wire would be caused to accelerate, giving a greater current, a greater force, a greater acceleration, and so on. This would oppose the law of conservation of energy. Looping the wire like this would double the flux linkage, and so would double the EMF for a particular speed of moving the wires through the magnetic field. These observations can be summarized as Faraday's law, which states that the magnitude of the induced EMF in a circuit is directly proportional to the rate of change of flux linkage, or to the rate of cutting magnetic flux. Also Lenz's law, which states that the direction of the induced EMF is such that the current that will flow in a complete circuit opposes the change producing it. This can be written as the induced EMF epsilon is equal to minus the change in flux linkage over the change in time. The minus sign is from Lenz's law, meaning the direction of the induced EMF is in the opposite direction to the change causing it. This part of the expression is from Faraday's law.